Hello, 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 hello,
Hello, Professor.
hello, guys. Thank you for being so prompt again. I, hello, hello, guys. You're so prompt. It's unbelievable. No, it's believable. I totally believe it, but it's very pleasant. Uh, and so you guys, you do get. I just want to confirm you when you come on. There's like a waiting room, right? And okay, and it says like something about physics, but it doesn't specifically say physics 204 or physics 203
Yeah.
or anything like. Okay, okay, right. Yes, okay, cool. Thank you. Okay. Um, oh, before we go we're going to go back to. Oh, good afternoon. Yes, good afternoon. Thank you. And we're going to go back to. We're going to go back to a thing on a spring today. But more people coming. But I wanted to I still have to give you a syllabus. I haven't done that yet. It's as far as procedures and policies, it's the same as I will give you one, but it is the same expectations as physics 203 if you took it at John Jay. And I want to continue with a thing on the spring today. But one assignment I want to put in your portal right now, bear with me, or one yes, thing I want to alert you to. So bear with me. Oh, and people are still coming in, excuse me. Pardon me, people are still coming in. Okay. Actually, while you're bearing with me, I want to put something in your stream, but actually we can get a jump start. We are going to go to thing on a spring today, but I do want to back up. This may help. Please, this will help with thing on the spring. So you may want to start by copying this down or seeing if it's familiar. But I'm just going to put something in everybody's stream. Okay. Okay, what you'll hopefully find in a minute, hopefully you'll confirm to me in a moment, in your stream, you hopefully just got an assignment that's called A Game, Your Best, or something like that.
Yes, it's in the portal.
Great, thank you. Okay, now what that is, I want to explain this very clearly. It's like this, it's kind of like a game take one that we put in yesterday and we talked about, but this is even more, maybe more important, more specific. This one literally has no due date and is worth 100 points. We're going to do this starting this semester. What this is a place for you at any and every or all moments, once we've got going in the class, wherever you want to direct my attention to first in grading you, you put there. Like, for example, say we're rolling along in this class and you've done some homeworks and some of you have done a ton of homeworks and maybe done a bunch of drafts of something and some of you have not or whatever. So some of you might have some better homeworks than others. But let's even say like we get to the midterm and we take the midterm and one of you and you rock it. And then we're getting to the final and you're super nervous about the final. You have a feeling it's all falling apart or something happened in your family or something like that. So like the best days are behind you as far as you're concerned. What I want to have here is an opportunity at any moment you put in that portal, and you can change this every day, and you can leave it alone every day until you worry. But in that portal, you tell me where you want me to grade first when I'm sitting down to do grades. Like, put another way, if I could only look at one thing, if you had an opportunity to shove one thing in my face to remind me or to represent you at your best in this class or your best piece of work, you would put that in the portal. It might literally be your midterm exam. If as we're getting close to finals, you want to make sure that I look at your midterm and again, before I even look at your final or something like that, whatever it might, or more realistically for many of you, like as we're going along, you might have a day in class that you totally rock and you know it, and you know I was really impressed or something like that, and you take a screenshot of like something you did in that day and put it in there, or one homework where you really worked hard and you just know that you broke through a wall, like you just clearly did not understand something before, but then you did get it. Any demonstration you can put in that part, and you can just, and there's no due date. You could switch it around. That's your place to tell me if I have one place to look for you to make sure, like, to protect your A, so to speak. That's where I would look first. And of course, then it goes both ways. Like by the time we get to the very end, if I'm scrambling and doing grades and stuff like that, it would be unfortunate if someone didn't even have something there, if like they've never done anything all semester that they could even put there as their best. They might want to then put a note there that said, I've sent you an email, I really need help, I'm panicking, or something. Like, but basically use that as your look here first portal. Does that make sense to people? Does that make any sense? You get
Yeah,
the
that makes sense.
Okay, great. Okay, thanks. All right, cool. And it really does mean that I will weight that as heavily as like anything you get it. I think you get it. Okay, I'm just looking in the chat, and then we're going to go to, no, this is the next class. Wait. Okay, wait. Yeah, this is confused. I don't know why this never happened last semester. So this is physics 204. If anybody, or I believe it is. If anybody shouldn't be here, well, I guess we'll find out. But yeah, physics 204. But all right, then stop me again if there's any. I will post. We're going to start going over this thing on a spring thing. There will be a new homework posted for Monday, but actually, as long as one last thing. And please stop me at any time if there's. Oh, and a ton of you have turned this in. Yes, thank you. I do see almost all of you have turned this in. That is great. We're going to talk about it now. If you did turn it in and we do corrections now that you want to turn in a better version, again, please feel free. Like just any work you turn in, the more work, the more I see that you're doing more work. It's all the better. Those of you who didn't turn it in yet, it's understood that you didn't after this class. Hopefully you take the benefit of the class and then turn something in, like turn this in before you do the next thing. But some people did raise last time. I know I want to go over the sheet, and I want to hear your contributions to the sheet, but I do want to back up and sort of discuss springs themselves for a moment, because yeah, we're just the sheet sort of dives in and assumes that we all get springs. Here, the deal with a spring, whenever we talk about a spring, we're talking about any material that's springy. Like there is all materials that are springy due to one extent or another behave like an ideal spring. And in the world, there's no such thing as an actual ideal spring. All regular springs are just to some extent springy, and some springs are better than others. What does it mean to be a good spring? Like, what does it mean for one spring to do its behavior more optimally than another? Well, it means to obey this graph right here on this page. What it means to be a spring is if you fix one end of a spring to a wall, like, so first of all, I'm making a spring horizontal now. So I'm not even worrying about gravity or any other effects. I'm just trying to isolate the effect of a spring. A spring is something that exerts a force. It's going to exert a force onto an object. So I put an object, an M, at the end of a spring. I fix one end of this horizontal spring to a wall. So I'm not going to be so one end is rigid, and it's horizontal, so there's no effects of gravity. Then the other end of the spring is the one that I want to watch, the one that I want to observe and pay attention to. I fix a mass to it, almost as a marker or as a thing to be paying attention to, but also because masses are the only objects in physics that can receive forces. When masses receive forces, they accelerate. So I'm going to observe the acceleration and the motion, et cetera, of this block. This block is on the end of the spring. Wherever that end is, naturally and normally, like wherever the edge of the spring just sits when nothing else is being done to it, is what we call the equilibrium position. We label it x equals 0. Like it's a displacement of nothing. It is the origin of our axis. and we've placed the mass there. And then we pull the mass out to some initial position where we're holding it, some initial displacement from equilibrium. We call that initial position x naught. We might put a number to it in a minute, but we don't need to. It's the initial displacement from equilibrium position. Like, again, we're focusing our attention on this mass, which is really like a mass point. The idea of a spring, what it means to be springy, like if a spring behaves perfectly, then what that means is that when we let this mass go at this displacement from equilibrium, when we let this mass go, the spring is going to pull it toward equilibrium, with an amount of force that is not constant. I mean, this is the key thing to springs, just to say to everybody why they're worth studying physically and mathematically. Springs exert a force, just like friction exerts a force, or gravity exerts a force, or tension in a string exerts a force. But most of those forces that we looked at last semester, they are constant as a function of position. That is to say, gravity, like the gravitational force on this pen that I'm holding right here, otherwise known as the weight of this pen. The weight of this pen, if this pen has a mass of m, then the weight of this pen is mg. Like if the mass of this is 2 kilograms, then this weight is 2 kilograms times 9.8 meters per second squared. This thing is 19.6 newtons of weight. That's its weight, mg. That's how hard it's being pulled to the ground. Why am I making a big deal of this? To make a point of contrast, which is that this pen is pulled with that amount of force, whether the pen is this close to the ground or this close, or this close, or this close. As the pen falls, we treat the force acting on it as essentially constant. That is not what happens with a spring. The reason we study springs, the first and foremost reason, is that springs exert a force that is variable as a function of position. Like it does, like the spring force does depend on position. That is a new piece of information. I mean, like it's new to springs, for springs. It's not true of gravity. It's not true of tension. It's not true of friction. But it is true of springs, and it's true of springs according to this graph here. What we're saying here is that the greater you pull a mass away from equilibrium, the farther, and again, I know this is boring, this is old news to some of you, but I just want to make sure we all have the same information here. The farther you pull the mass away from the equilibrium position, the greater the force of restoration exerted by the spring. It's such a nice, clean relationship. Like it is a relationship. There is variation there. So the number does change, but it changes in as nice a way as possible. It changes in a linear fashion, in a directly proportional fashion. That is, when the spring is not displaced at all, when the mass is not displaced at all from equilibrium, when x equals 0, the force is 0. When x is pulled out to, like, say, 1 meter, then the force is something times 1. When the mass is pulled all the way out to 2, then the force doubles. It's whatever that original something is times 2. What do I mean by something? I mean the slope of the graph. I mean the constant of proportionality. I mean this. I'm saying that if you were to graph force as a function of displacement, it's like y equals mx plus b, where b is 0. It's a linear relationship. The slope of that line is what we call k, the stiffness of the spring. K is K is the number of newtons of extra force you get for every meter of displacement. So K is always measured in newtons per meter. It's the stiffness of the spring. One last thing, and again, this is technically, whether this is review or clarification, this is just a background on the sheet of how springs work. I still haven't told you why we care about springs yet. I would like to tell you why we're going to care about springs in this class. And we're not going to just talk about springs like for the full semester. Springs are actually our gateway to, well, I'm not going to get into that now, but for the moment, I just want to say how springs work. Springs work like this. But the law governing springs, last thing to say, and tell me if you want me to go back on this sheet. The law that governs springs has a negative sign in it. I know I said this Monday or 2 days ago. The negative sign really means that really the graph, if you really want to be technical about it, truly the graph really looks like this. Not to, and I don't mean this to confuse people, but it's really in that quadrant because the direction of the force necessarily is always opposite to the direction of the displacement, just meaning that the spring force always wants to restore the mass to equilibrium. So if the mass is on the right side of equilibrium, the spring will pull it to the left. If the mass is on the left side of equilibrium, then the spring will pull it to the right. We are assuming something. Oh, this may confuse people. I'm saying left and right interchangeably like this. Like I am saying, you can set up your coordinate system any way you want. You can call positive, you can call right positive, and thereby make left negative, or you can flip them. But I am assuming that the spring is sort of free to move both directions. So what I am assuming is, and tell me again if you want me to go back on the sheets or faster or slower, please, because I will lose my. Okay. So one thing, I'm just defining what I mean by a spring here. And this is kind of, so I'm saying what it would mean to be a really good spring. One spring is better than another if it can extend about as much as it can compress, right? So you could pull out one end or you could push in the end, and the end is where the mass is. So that's why the mass can go like left or right. Springs work when we ask them to do this only to a tiny extent. Like this is really the arbiter of springs. Like you want your spring to be very long compared to the amount that you're asking it to extend or compress. The more you want a spring to extend or compress, the bigger you want the whole spring to be. You don't want so in other words, in this problem that we're about to solve or that we're solving, where the spring extends like 0.15 meters, 15 centimeters from an equilibrium position, for this whole thing to actually be realistic or to work, we would have to assume that that spring itself is a heck of a lot longer than 15 centimeters. Like maybe it's like a meter long or something. Okay, that's how, and we assume on top of that, number 3, that its curls, its coils, its tightness is uniform, meaning essentially the same tightness over here as it is over there, the same number of turns per unit length. the more any of those properties is observed by any given spring, the more springy it is, like whether it's a mattress spring or a spring inside some material that you don't see. But to be springy is to obey F equals negative KX. And the smaller displacements that you study for the bigger the spring, the more you'll find F net equals KX to really be a straight line like that. Okay, like we just drew on the last page, right? That's that. So a spring is a last thing to say. Oh, sorry, last very important thing to say. Oh, we got to, okay. The last thing to say about spring. Now this, okay, I'm going to make a little bit of, all right, I'm going to make a little bit of a mathematical big deal of this item number 2 here on the board. I'm going to say, so there's going to be like one more sheet here, one more page. I'm going to say one mathematical thing. Then I'm really going to shut up and turn it over to you to have a group discussion about the sheet. But I'm just again, just trying to put everything in perspective for a new semester. What I'm saying right here on this sheet, on this screen, is okay. Number one, I keep calling it the spring force, but to be a word that's actually preferred, that it would be, I want you to know, it's even better than calling it the spring force or looking at a spring. It's even better to call it the elastic force, not to be technical, but the reason it's almost better to call it the elastic force from here on in is from here on in, we're going to picture today a spring going back and forth. Even I don't think there's anything that exciting about like sitting there and analyzing a spring, although you are also doing it in lab. Like it's going to get maybe a little headachy after a while to sit there and be so obsessive about a spring. Why do we care so much in physics about a spring? Well, one thing is I want to make clear, it's not really that we care about a spring, it's that we care about elasticity in general. Like whenever we're studying a spring, what we're really studying is the nature of bounce, like the whole idea of bouncing or what it means to be bouncy or springy or elastic. That idea, or to bounce back. Why do some materials, like when you squeeze them, they bounce back and they restore themselves, like the bumper on a car, whereas other materials just deform, like you hit the metal of a car and now it's crumpled and you're toast, right? I want you to understand that when we're going to get very mathy about how a spring behaves, and it's going to, like rubber. I'm sorry. Yes, absolutely. Like rubber. That's awesome. Like the math is going to start getting very mathy. I love it. And I know that we've all seen physics before, but it's going to get mathy even for what you saw in 203. And it's going to get abstract. And a question can come up like, oh my God, like, are we still talking about freaking springs in this class? That might come up. And I want to just alert you in advance that whenever you think we're talking about springs, really say to yourself, what we're actually talking about is springiness. We're really talking about what it means for something to be bouncy or rubbery or elasticy. And that down, ultimately, we're doing that because down to the molecular level, what it means that atoms and molecules are like they were, like electrons repel off each other, and molecules like come together or bounce off each other, depending on their electronic like arrangement. And the way in which and we're ultimately going to get to this in the class, even the way electrons or molecules do or do not bounce off each other, that elasticity is so pervasive in all of nature that it requires a lot of attention. So I'm going to call the spring force, I'm going to call it the elastic force to kind of remind you that we're talking about elasticity in general, even in places where you don't see a metal spring. Okay, that's number one. Number two, the elastic force, this F equals negative KX force that you use to get answers in that thing on the spring sheet. The force is worth studying. Number one, it's variable. We already said that, like it's not a constant force, so it's got some math associated with it. But much more to the point here, number two, I want to say straight up, it is an example of what we call a conservative force. That is a big idea and going to become a very big idea in this particular class. You've seen one conservative force before in your life in physics, and that was gravity. That's the only force you've seen before that's conservative. This is the second, but it's different from gravity. So let me be clear. Okay, this is kind of a heavy idea. We're going to unpack it as the course progresses. I'm giving you the title of it first, or and again, you've seen a version of this before, but not put as mathematically. Um, a conservative force is a force that does a conservative force is one that does zero net work around a closed path, or in other words, around a round trip or around a loop. A conservative force is one that does a total of no work whatsoever, bringing you here and back. Okay, there's a lot to that statement. So, a quick reminder, a quick refresher. Part of this is a sneaky way of like reviewing or unearthing old physics 203 concepts, not assuming everybody remembers them perfectly or even knew them perfectly or anything, but that's what's sort of happening here. There's an and I'm not going to write this down now because I don't want to get myself too bogged down, but there's an old concept in physics called work. You might remember. Strictly speaking, work is a force times a displacement, right? Like when you do work on something, you exert a force, you push it through some number of meters. We'll review that again, but I am saying it. To do work is to exert a force through a displacement. If your force is in the same direction as your displacement, you're doing positive work. If your force is in the opposite direction from displacement, you're doing negative work, right? Because it's like a product, like a negative times a positive equals a negative times a negative equals a positive times a positive equals a positive. So I'm saying that some forces like friction, if I'm pushing a book across a table and there's friction from that table on the book, right? So the book is moving to the right, friction acts to the left. I'm pushing the book to the right, friction's acting to the left. I'm pushing the book to the right, friction's acting to the left. So friction's doing negative work, negative work, negative work. What's it doing? It's sucking kinetic energy out of the book. It's slowing it down. If I push a book to the right, friction does negative work on the book, slows it down, takes joules away from it, right? But then if I turn around the book and start bringing it back to the left, friction now flips and is pointing to the right. So if I take a book across a table on some big round trip, I push the book out to the right, and then I bring it back to the left. Friction does negative work on the book on the way out, and it does negative work on the book on the way back in. Friction's always doing negative work. It's always slowing it down. It's always taking energy away from the book as I go there and out. Friction is not a conservative force, because around a round trip, friction just builds and builds and builds its impact. In the case of friction, it's like negative impact. If I were pulling a book with a string, it'd be the exact same argument, but with positive work rather than negative. Like a string is always helping a book along, whether I pull the book to the left with the string or that I turn around and pull the book to the right. The string is always just doing more and more positive work on the book, not a conservative force. But so I'm saying this to everybody now, whether you think you've heard this before in 203 or it's the first time, I'm saying to everybody, I'm giving examples right now of non-conservative forces because I want to highlight the specialness of the spring force. Okay, most forces are non-conservative. It means they do a net amount of work, whether positive or negative, through round trips. Gravity is conservative because gravity, if I'm pulling something up, I'm pulling something up. Well, gravity is still acting on the object, right? Like that's why I have to be pulling it up to make it. So as something's going up, gravity is pulling down. As something is displacing up, gravity is pulling down. So gravity is doing negative work on an object while it goes up. Say I don't want to hurt myself, but say I throw something right now. I throw something. It's flying up. It's flying. It's like velocitizing up. Gravity is pulling down on it while it moves up. Gravity is doing negative work because it's pulling in the opposite direction. And that's evident from the fact that the object is slowing down while it moves up, right? So on its way up, gravity is doing negative work, slowing it down. Fine. But then the object starts coming down in gravity. Now, this is fundamentally different from what happens in friction or in tension or under the normal force or something like that. When something's falling down, now it's displacing down and gravity is continuing to pull down. So gravity didn't flip at all. Like friction flips. When you flip your velocity direction, friction flips accordingly. Gravity is just always pulling down. There's always this equilibrium place associated with gravity called the ground that everything is coming towards. So on your way up, gravity is doing negative work. Then on your way down, gravity is doing positive work. And work is force times displacement. So if you go up some displacement and then you come down the same displacement, if you end up where you started, for that whole round trip, gravity will give you back everything that you started with. Everything that you lost, gravity will give you back. Friction does not do that. Tension does not do that. The fancy mathematical way of saying that we'll break down more as we go through. But what I'm saying here is that technically the closed path integral of the force with respect to the displacement is zero. I mean, again, some of you know those symbols, some of you don't. We're going to do all those symbols together in this class. We will. But in English, what I'm saying is number two. I'm saying a conservative force, call it FC, is one that does zero work around a round trip. I'm going to go to the next page. Tell me if you want me to go back, and then we really are going to. So the spring force is conservative. Okay, wait. I think it's time for me to shut up and for you to talk about the sheet. But let me look in the chat. There's something in the chat. Sorry, hold on. Oh yeah, like rubber. Yes, absolutely. Awesome. Okay. So yes, I've talked enough. I don't know if that was clear enough, but let's turn to the sheet and let's have you. Did we go? Oh, I'm sorry. Did we go over any of the answers yet? I don't remember.
I think the
Nope.
first two, but not in detail. Like you just like said the answer really quickly.
Oh, sorry. Okay, right. That makes sense. All right. Thank you. Right. So, well, so I think for the first one, so the first one's asking force. Right? I mean, yeah. So hopefully, what I'm saying today helps this a little bit more. I'm saying in the first one, wait, I better get the sheet. But I believe the very first question is what's the force exerted, right? Yeah. Here we go. Yeah. Okay. So, and So I don't want to under or over talk, but just based on like everything I was just babbling about for the last 15 minutes, is 1 and 2 clear to people? Is this, I mean, did I? Oh, yeah. I mean, are there any, I guess I did say them on Monday, but I guess I want to make sure if 1 and 2 are clear, and if now, like, let me publicly recognize again, I don't think I really taught springs last semester. I mean, I realize that, and I don't, if you had a different class, you may or may not have seen springs. So now I'm just saying, I think I've told you all everything you need to know about a spring to go forward. Like based on today, are there any questions about this or springs thus far? Or should we just keep going? I'm losing my.
The first two questions are clear.
Okay, great. That's what I'm asking. Perfect. Thank you. Okay. Should I do question 3 or does somebody want to do question 3? Maybe the.
I can talk you through 3. I'm not sure if I got it right, but I did it.
No, perfect. Great. Okay.
So I basically used the same thing we did for 2. So mass times acceleration equals negative kx.
Right. Okay. I'm going to write it this way, but yeah, I totally agree. Awesome.
Yeah, so I plugged in 0.3 kilograms times acceleration, and then negative 200 newtons per meter times 0 meters.
Yeah, that's the key. Yep.
Okay, so, and then if you do that, you get 0 meters per second squared for acceleration.
Exactly. I could not agree with you more. That is awesome. Yep, that is awesome. I could not agree with you more. I could not even add anything to that if I wanted to. Yes, that's exactly right. So, and that's just highlighting. So good. Thank you very much. Awesome. And so now we're just proceeding here step by step. But one thing that highlights right away, notice that we solved for acceleration now twice at 2 different spots. Like no big deal, perhaps. Like, I mean, exactly what Alyssa's saying. I mean, when X is one thing, A is one thing. When X is another thing, A is another thing. But notice that means that acceleration here is changing every point in space and every point in time. Like acceleration seems to be continuously changing. Now, if we are just observing a regular spring, it starts with minimum speed and maximum acceleration. It starts moving in toward the equilibrium where it seems to have minimum acceleration and I'm guessing maximum speed, which I guess then brings us to question 4. But that's very good. Thank you for question 3. That's great, Alyssa. So does someone else? Now question 4 is like a leap now. In fact, wait, this class. Oh no, we will get through this. Yeah, okay. Question 4, now we have to take sort of a leap. But does anybody have any thoughts about question 4?
Thought you mean answers?
Sure.
Okay, so first you gotta, because last time you said you're not gonna provide the SPE, you want us to figure it out,
Oh yeah.
right?
Right.
So for that, it's simple. Like you can just use like kindergarten mathematics to calculate the area of the F equal to negative kx, or you can use calculus like the derivative to get the half kx squared
Nice.
for the SPF, you know what I'm saying, right?
Good.
And use energy convention, lift equal right the kinetic energy and the potential energy from the spring, and you can get the answer is like, I think I calculated wrong, but it's like 3 point something.
Yeah, no, I think you're right. I think the
Okay.
ultimate answer to this one, yes, very good. And I forgot if we talked about this or not, but yes, that's very good. And I do agree for everybody that the final answer to this is like approximately 3.87 meters per second. We'll do it. But yes, that is right. And I do agree with everything that was just said. Thank you for reminding me that you derived all of that. I will do that on the piece of paper. But yes, we're now going to turn to energy conservation. We're going to make use of the fact that the spring force is conservative. Not only is that correct, and so we're going to use potential energy, which I do want to discuss here for a moment or review. But one thing to everybody, notice in the first couple of questions, we're doing Newton's laws, F net equals ma. That law never stops being true, but sometimes it it stops being as directly useful. Like, if you're doing homework by yourself, if you've never thought about this question before, or if suddenly this appeared on exam, even if you felt okay with questions 1, 2, and 3, question 4, you might get stuck on, or all of a sudden it might seem unfair. Like, why were we doing F net equals ma? Or why are we focusing on acceleration for the first 3 questions? And then suddenly somebody correctly in the class, Mr. Zhang in the class, is now talking about energy suddenly. It's a very fair question. Why did we just suddenly shift gears and start talking about energy? But here's the reason, just to tell everybody, like, how you would know is a habit that you want to develop eventually in physics. But the reason is that the acceleration is not a constant. The minute we just realized that acceleration was differing from spot to spot is a strong suggestion that we better move away from our constant acceleration models. Like, we're going to not be able to get very far with 1/2 at squared or any of those equations, because we just showed ourselves that the acceleration is changing. We have to think in a different model. Like, we have to find something else that's constant. And the very next thing that we always turn to when acceleration is not a constant, we ask ourselves, is energy a constant? And energy conservation, we ask ourselves, is energy a constant? And the answer is here, yes, because the only force doing work is conservative. So that does end up meaning that energy will be, in fact, conserved, like Mr. Zhang said. But the specific implication of that is this. Sorry. Tell me if I'm going to turn the page, unless, well, tell me if you want me to turn back. I'm happy to turn back. And again, tell me if I'm going to turn the page just to keep from boring everybody, but tell me if you want me to turn the page back, or tell me if I'm going too fast. But I'm going to turn but I hope people are writing these things down. I mean, this is going to get into physics, but Okay, I want to make, we're going to do question 4. Question 4, the answer is indeed going to be 3.87. Not trying to hold anybody in suspense over that, and some people might have gotten that very fast. You might even say the answer is 3.87 because you might do something like square root of you might do square root of 200 times 0.15 all over 0.3, and you might do it in one line and get 3.87, and you'd be right. But I want to explain to everybody what you did in that one line. Because I'll also say, by the way, for anybody who's the answer to the next one, and I'm going to work this out. I'm not trying to skip, but the answer to this one is going to be 3.87. But for a reason I want to show everybody and also warn you that that reason, if you do it properly, will also get you the answer to the next question, which will be 0.095, I believe, 0.095. Whereas there's very common wrong answers to the next one. It's very easy to misunderstand this one and then misapply it to the next one. So just to keep things in perspective, I do think the answer to this one's going to be 3.87, but here's how I think about it. Here's how I get 3.87. I say, all right, so I'm turning back these pages for a second to explain. I say I've just noticed that the acceleration on this thing is changing continuously from spot to spot, continuously, like not in chunks, but just like smoothly changing. That means all of my old constant acceleration equations and understandings go out the window. There's no constant acceleration to be found here. So there's no like 1/2 AT squared kind of analysis. So I asked myself, all right, well, I need a different thing that remains constant. Always in physics, you're looking for the constant underlying the apparent changes. So I think is energy a constant here? Well, in fact, every force that's doing work on this object, there's only one force doing work, and that's the elastic force. And it turns out that every force doing work here is a conservative force. Like we just said that a couple of pages ago. So that's the condition that needs to be met. It's true, any system that is only being worked on by conservative forces will conserve energy. Now that almost sounds like circular reasoning. Like what does that even say? Well, it says it is circular reasoning. It's just an application of the definition of conservative force. But what it means is, like, let's go back to gravity. Think about gravity for a second. Gravity, when you go on when you undergo a round trip under gravity, the net work done on you by gravity is nothing. So whatever energy you start with in a gravitational system, whatever energy, if I throw something up and it falls back down, whatever energy it started with, like whatever speed I gave it originally to throw it up, if I threw it up at 50 meters per second, so it had that much kinetic energy and it's going up, it's losing kinetic energy, it gets to the top. Eventually, it's going to come back down to me and get back the exact same amount of kinetic energy that it started with, right? We can rely on that because gravity is conservative. So what that means to us, that gravity will conserve the amount of energy in this object, it means that we can invent this shorthand. And this is what we do. We invent a shorthand. Whereas before we always said what work is transfer of energy. Like I do work on you, I give you kinetic energy or I take it away. What we say now is under gravity, if I throw an object up at 50 meters per second, when it gets to the top, right at that moment, it doesn't have any, when it gets to the top, it doesn't have any energy at all. It just ran out of all of its speed. It has zero energy. But I know that it's about to come down. I know that if I let it go, if I don't hold it there, it's going to come back down. And that I know that by the time it gets back down to where it came from, it will get back all the energy that it started with. So I can predict even before this thing falls, since I know how much work was done on it to get it up there by gravity, I know how much work gravity is going to do on it to get it back. Like I couldn't say this with friction or with tension or any other forces. I can't make that kind of prediction with non-conservative forces because no matter which way they're going, they do more and more or less and less work. But with gravity, since I know that over a round trip, it has to give back whatever it took, or it has to take whatever it gave back, then any trip that anything makes under gravity, I can call in my mind the first half of a round trip. I can say that when this object is up here, even though it has no kinetic energy, I know how much kinetic energy it's going to have if it completes the second half of this round trip. So I can say that it's storing that energy up here, and I could call it potential energy. Hey, this is the thing I want to be slow and pause on today. I know all of you have heard of potential energy since 6th grade or something like that. I'm not pretending at all that this is the first moment you're hearing of potential energy. But I did ask Yabo, and I did ask you guys last time to be careful about potential energy. And I'm glad he was, very glad, because it's worth thinking about from the bottom up. Like when we start all these concepts, we don't need or have any notion of potential energy. But when it comes to something like gravity, something that's conservative, we start saying to ourselves, oh, some object that's up here, even though it isn't moving at all, even though it's sitting still and has no kinetic energy and it has no ability to do work, nonetheless, we know that it's going to fall. We know gravity has an equilibrium associated with it, the ground. We know that this thing could fall, and we know exactly how much energy it will have when it falls, when it arrives at the ground and finishes its fall. Since we can know that in advance, because gravity is conservative, since we can know that in advance, we say that this object up here, sitting at this spot, has stores the energy as potential. We say the object stores the energy as potential because it's really just a prediction of how much energy the object's going to have when it gets to the ground, or it's a recognition of how much energy was taken away from the object in order to get it up here in the first place. We say all these statements only because gravity is a conservative force. You never hear of anything called like the potential energy due to friction or the potential energy due to a wall, like normal force. Potential energy is only a concept that is only associated with conservative forces, and it's tightly associated. Like there is a gravitational potential energy due to the conservative force of gravity. Similarly, we're going to say today that there's such a thing as elastic potential energy associated with the elastic force exerted by a spring. Only conservative forces are said to store energy. And they're only said to store energy because it's a shortcut we're making, because we're writing down a prediction before waiting for it to come true. When we say that gravity stores energy in the form of gravitational potential energy here at the top, you might well ask, well, where is that energy being stored? Like, is it in the object? Is it in the earth? Is it in the space between? All very fair questions. Most physicists would probably say it's being stored in the system, in the earth object system. But what I say, at least for these purposes, is I say where the energy being stored is in our mind, in our memory. It's just it's not just, but it is a mathematical device for just keeping track of things, potential energy. And it's only useful or relevant to conservative forces. All that being said, what I'm saying is, and I know I'm taking a long time, but just we need this concept to be fleshed out for this course. I'm saying, oh, well, yes, I'm saying then that when we say that a system conserves energy, when we say that the only forces doing work on it are conservative, what we mean is that if we look at any given place, any given spot, any given location, that's why this says, okay, mechanical energy is conserved from place to place. When we say that energy is conserved, and we're going to say that. I mean, Yalbo, and I hope I'm pronouncing it right, is already saying correctly for this problem. We're going to say that this spring system here conserves energy. When we say that, mathematically, what we're saying is pick any one spot A, like A. By A and B, I mean two possible X locations. They're just two locations, X equals A and X equals B. In the case of, say, this spring, like they could be, the two places that I mean by A and B could be X equals 0 and X equals 0.15 meters, something like that. But whenever you're talking about energy, you're comparing two places, 2 points in space, like not points in time, points in space. And you're saying that the total amount of energy at any one place, all the kinetic plus all the potential, is the same as at any other place. That's what energy conservation means. It means the total sum of all kinetic and all potential at one place is equal to any other place. And we're almost there now. And what do I mean by potential? Well, remember, potential was just that memory recording or that knowledge of how much work was going to be done by gravity on the blocks way down or whatever it might be. In other words, oh, okay, this is a mouthful. Take a moment to get this. I'm going to step away for 1 second. Just let that sink in for a second. I feel like I'm talking a lot, but I'm going to go one more page here. If it's okay, I'm going to go one more page and just bring this back to show the 1/2kx squared thing, and then turn it to you. This is actually a perfect place to pause for everybody. I've been talking a lot. This is getting abstract. And this is typical. I've been saying a lot about things that a lot of you are like, I got the answer like last night, and you're saying all this stuff, Yaverbaum, and I don't see what it has to do with the answer. Or some of you are like, I didn't get the answer. I don't even know what's going on. And all the stuff you're talking about does not help me know what's going on. Both of those might be true right now. In theory, I'm in question 4 right now. But here's where we're going to take a break and see how this all, like, I'm going to turn it to you guys again. Oh, and I'll look in the chat in 1 second. I'm sorry. But when I want to turn to, this is, what I'm filling in here is something that Yaobo, and again, I hope I'm pronouncing the name correctly, that he said before. I'm expanding on that in a big way because I want to make sure everybody has this whole concept before we get too far in physics 204. The whole concept being really how conservation of energy works. And yeah, it's going to start getting mathematical again. So I'm reminding you, or I'm saying that strictly speaking, work, the concept of work in physics, well, it's force times displacement, but really it's the integral of force with respect to displacement. Now, we got to deal with integrals in this class. We're going to be mathing this class. I want to say again, some of you are like no problem with integrals and want to see more of them in your life. Many of you are totally intimidated whenever you see an integral, and maybe you don't even know that you are. I was. Anytime I saw an integral, and I was a physics major, okay? But for a long time, the minute an integral was in something, I secretly knew that I had no idea what was going on. And it would make me nervous and I'd have to work around it and stuff. I am not pretending that some of you are not in that place right now. I'm here to hopefully break down integrals for people and make them more manageable. But I can't do it all at once. I can't do it on the first day. I'm just going to say right now that strictly speaking, work is defined to be an integral. Because an integral is what you do when you add up lots and lots of small chunks of something to make one big chunk. Like, sort of quickly, if you can understand that work is force times displacement, then think of it this way. If you do a little bit of displacement and there's a force acting on you, you could calculate the work for that little bit of displacement. And then if you did a little bit of displacement more and there was a force acting on you, you could calculate the work for that little displacement. If you wanted to know the total work done throughout a whole big displacement, you might want to divide the whole big displacement into lots of little chunks of displacements and add up the little works over each little one. You might want to do that if you notice that the force that you had to deal with the whole time was changing, right? Work is force times displacement. But if at every little bit of displacement, you have a different force to work with, how can you there's no one number to multiply through the whole thing. So what you do is you divide the whole into a bunch of little parts. You do force times displacement, plus force times displacement, plus force times displacement, plus force times displacement. And if you take that whole process to the limit, like if you make those little pieces so small that for each piece, the force is barely changing at all, and they're so small that you actually have a real ton of pieces to add up, take that to the limit where it's an infinite number of infinitely small little pieces. That's what an integral is. So work in general is the integral of force through displacement. It's like saying, add up force times displacement, plus this force times displacement, plus that force times displacement, add them all up so you can account for the changing force possibility, and you'll get the total amount of work done by any force. I'm saying here, potential energy is the work done by a conservative force. Like it's the work done it's the work that the conservative force is going to do to bring the object back to equilibrium. Like if the force is mg and you raise an object to a height h, then on the way down, gravity is going to do work on this object mg times h, mgh. And that's why we say, oh, well, right here, as the object's even just sitting there, it's storing potential energy, mgh. It's just a prediction of how much work is going to be done by the conservative force to restore something to equilibrium. Well, if the conservative force exerted by a spring is kx, I'm getting rid of the negative sign. Don't worry about the negative sign for the moment, Alex. But if when you let a spring go, the spring pulls the mass in toward equilibrium, right? So the spring is pulling that way. You can worry about the negative sign if you want. I'm not worried about it for the moment. But the point is, if the spring force magnitude is kx, integrate that force with respect to dx to find the amount of work. I want everybody to do this now. I'm going to look in the chat. Okay, wait, I am going to look at the chat. Sorry, it's crazy. Hold on. Oh, great. Oh, awesome. Okay. Yes, and I may, right, I see the private chats and I may take advantage of that in a second. But what I want everybody to do before we go any further, and even if we only have 10 minutes, is do that integral right at the bottom of the page. Like I want the integral of kx dx. It's like a math question. Even if you don't think you know what the physics means, just if you were given that, if you assume that k is a constant, k is just a number, but x is the variable, it's the integral of kx dx. Can everybody take a moment to just do that integral? You can either share it in the chat or tell me in the chat when you have an answer, or yeah, in fact, let's just say that. Great. Awesome. Yes. Awesome. And keep going. Even if someone's already put in the answer, I want everybody to either put in the chat the answer or raise your hand to say the answer, or just make sure you could do this. I want to make sure everybody's together with me. But I do see two things in the chat, and I appreciate it. Yeah. What? Oh, very interesting. Oh no, sometimes we do. We're going to talk about that plus C. That's very good that you brought up the plus C. Oh no, we're not even going to, I don't want to dismiss that plus C. I care about that too. Some of my best friends are plus C. No, that's a good point about the plus C. But all right, well, I'm going to go. I've got two people here that are weighing in on this. Does everybody, I mean, is everybody cool with?
Yes, we are cool with it.
Okay. Great. That's good enough for me. Okay. Then now, and I'm going to say, okay, so strictly speaking, in fact, let me go a step further since I got, oh, good. And I see the bright thing. Oh, good. Thank you. Awesome. Now, okay, so the part C, let me actually address that. Let me be more specific. I'm saying this. Okay, actually, yes, I'm glad we're doing this, and I appreciate you. See, your participation really does help because we're going to do this one step more carefully here, or one. This will help us and now this all may seem like a digression, but we're actually saving a lot of time on something we have to do later. But here's what I'm saying then, to be specific. So I'm saying, look, kinetic energy is always 1/2 mv squared. It is in physics, at least until Einstein. Kinetic energy is 1/2 mv squared. It won't let you down on any exam in this course or anything like that. But potential energy is different equations for different contexts. Like on a practical level, the reason I'm spending a lot of time on this today is potential energy is a hugely important concept, and it turns into the concept of potential in circuits, which are part of this class. Like we're getting to electricity and magnetism and electronic circuits and stuff, believe it or not, even at this pace, we are getting to that stuff. And what you call voltage in a circuit is just a trade name, is just a casual name for electric potential. Okay, so potential is a concept that's going to carry across all these disciplines. And potential, and there's different formulas, different equations for different potentials in different contexts. You don't want to just memorize potential as one equation or one thing. It is a concept. What it is the total amount of work done by a conservative force in order to restore a system to equilibrium. Like that's what potential energy is. So specifically, let's look at what it would be in this case of a spring. The potential energy of a spring would be the amount of work that the potential energy stored in a mass at the edge of a spring would be the amount of work that we predict that the spring would do in order to bring that mass back from its initial spot of 15 centimeters to the spot of 0, the equilibrium position. Like by definition, I'm saying potential energy has to be the work done by conservative force in order to restore to equilibrium. So in this case, strictly speaking, that would be the integral. Now, here's where I'm going to address that plus C business. He's totally right that there was, when I just asked you guys to do an integral, I was like casual and I just presented it as an indefinite integral. So strictly speaking, the answer you get should have an arbitrary constant. And I agree with that. And I agree with my math colleagues that if I just give you an indefinite integral, there is a plus C in the answer. But let me be less casual and give you the actual definite integral that we're talking about here. We're talking about integrating something from x naught to 0. That's literally what we're saying. Well, how much work is going to be done from that spot x equals x naught, which, eventually will be a number, 0.15. But that spot x naught coming into 0, we want to know how much work would be done by that force. Now I will be careful. I will be careful about the negative sign and everything, as long as we're going to do this carefully. I didn't want to get too crazy too fast, but this class is crazy. The pace is just, no, it's not great, but this is good. The questions we're getting are good. So I'm saying, in fact, I'm going to turn it to you guys again. Even if you think you already got an answer, even whether you're following or not is actually perfect for everybody to try. Just look at this integral that I just wrote. I know we've got 5 minutes, but just pretend you just saw this in a math class and be careful with negative signs, and follow whatever your rules are. but to see what you get for this on its own terms. And this is the last thing we'll do today. This is the last thing we'll do today. And we'll continue with this on Wednesday. And and someone did volunteer to show their work for the next two, which I totally appreciate. We might pick up with showing their work next time. I don't mean to cut those people off or that person off, but I think we're going to end here. But I want everybody to try, even if you already know what's going on in your mind, you think you know what's going on with the indefinite integral. Please try this definite one and satisfy. You've done something right if you can get an answer that doesn't have negative signs in it, I guess is what I want to say, really. Yes, and I'm going to take these. And yes, I agree about the triangle area. Yes, and yes, I'm going to post. Oh, two quick things. I'm going to post these notes right away, right after this. I'll call it in your Google Classroom. I also may assign one more sheet of homework, even if we don't. If I do, just do that at your pace for next Wednesday. Like clearly for Monday, we're going to keep talking about this sheet. And honestly, I don't think we won't get past the sheet Monday. So just do your best on this sheet. But I will also post the YouTube recording of this thing after tonight. And hopefully you found, someone suggested it, I don't remember if it was this class or the other. Hopefully you found that the Zoom link is easier to find now in Google Classroom. I'm hoping it's a little easier to access and get on anytime. And same thing with the YouTube link. But okay, since I'm talking so much and this class is about to end, here we go. I'm looking in the, yes, right. And is that to everyone? Yes. So just to be clear to everyone, strictly speaking, the integral that we're talking about here would be integrating that Hooke's law force, that one that has a negative sign in it, but integrating from that initial or amplitude position of x naught to 0. So what we really would get is you would get this, which is this, which is this, which is this. And what this just shows, I guess that shows strictly, that's something that, right, I do think it's important to derive and not just memorize it, saying that just like the gravitational potential energy is mgh, because that's just the work done by gravity to drop from a height h, the spring potential energy is 1f kx squared, because that's just the work done by a spring to restore you from x naught to 0. So the last thing I'm writing today, we'll just leave it at this for now, but just to sum up where Mr. Zhang got his answer originally and what other people are doing right now and what Justin did, just to sum up, I'm saying therefore, 3 dots means therefore. I'm saying in this case, and we'll leave it at this. And again, I know many of you would have written this down right from the get-go or something even simpler. I'm just trying to show you why what you're doing is right so that you have this for times when things are not quite as comparatively straightforward. Like we're saying this, and then we're saying for question 4, we're literally saying it, but this is what we'll pick up next time. Sorry. We're saying like, then right, this is why many of you would have just written down, why many of you would say correctly for 4, you would say something like, okay, 1f kx squared equals 1f mv squared, and then you'd cancel out the f's and you'd solve for v, which is what you should do. I just want to emphasize, just starting with this little thing that I scrawled in the lower right-hand corner, that really is not a correct way to begin, right? Like it turns out to be true here in this case, but there's no law that says kinetic energy is always equal to potential energy. What we're saying is a law is that the sum of kinetic plus potential at any one given place must be equal to the sum of potential and kinetic at any other given place. And we set that up as our law. And then we apply to the particular circumstance, like the particular circumstance here has us comparing 2 places, one of which has a speed of 0 and the other which has a position of 0. So we got to cross out terms and end up with this simple thing down here. I'm just sort of warning you that if you go to question 5, which I think we're going to show somebody's work of that next time, if you go to question 5, you got to start similarly with this whole comparison of 2 spots and then cross out carefully. Both those terms don't cross out in term 5. I mean, in question 5, if that means anything. But okay, that's enough. It's 1:30. Wait, whether is money on. Oh, yes, absolutely. No, absolutely. First of all, again, I will post this and I'll post a video. But Monday, we are not moving on until we finish this sheet. We are going, I want to say this to everybody, and it will be less boring too. I'm afraid if I'm boring people, but not all sheets will we go through step by step, but this sheet, we are going through the whole sheet step by step, wherever you all are in the material. That's what we're doing next Monday. We're not moving on until we have to get to the end of this sheet. I don't know if is it? Yes, no, we are definitely going over the rest of this. Like that's the next thing we're doing on Monday. And I'm saying that emphatically because I think it's a fair question that someone put in the chat, but I'm also saying it emphatically because maybe that's not always true. But with this assignment, we all carefully have to know it before we move on. Sorry. So if there are any other questions or and again, if I post homework too, then that means just if you're up to it, go to it and you've got something to do. You're always just trying to go to the next thing. But if I don't post it, keep working on this. But if you want to just say goodbye, how about we just say like when you're about to leave, just like shout goodbye or put on your video and say goodbye, just like right when, so I can just know that we've satisfied our experience. Because I'm good if you're good.
Bye.
Thank you. Bye. Bye.
Bye.
Okay.
All right, thank you.
Bye.
Bye,
Thank you.
Professor.
Thank you.
Bye. Thank you. Thank you. Bye. 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 Thank you. Awesome. Thank you. Awesome. Thank you. Awesome. You guys are good. Hello, hello. Aisha and Andre.
Are you
Aisha.
gonna stay here for a bit? Because I'm just trying to figure out this last part.
Oh, okay. I can pause. If you have, yeah, I mean, I do have to go get but yeah, if you either want me to pause for a second so you can look at it, or if you want to ask me a question, I can do for a second. Yeah.
It's like it's almost about a click.
Oh, okay. Okay. So that's fair. But do you want time do you want time to think or you want words from me? I mean, do you want me to say something or be quiet?
No, it's fine. I just need to just look at this for a bit.
Oh, okay. Sure. Okay.
All right, Professor, I've got it. Thank you.
Oh, no
Well,
problem. Thank you.
It
No
clicked
problem.
to finally click.
You
so-
are a good man. I'm impressed. That's cool. Good talk. That's good.
I think no, because all of the explaining, you said it was slow, but for me, I was just trying to go through it because it was my first time with like the springs and doing this. So now that we've gone through it, I get it now.
Oh, good. No, that makes me very happy. That's great. No, and I'm sorry when I say it's, I don't think any of this is slower. I shouldn't say that. No, I'm glad. That's good. That's good. That's good. All right, cool. All right.
So I will see you Monday.
Yes, see you Monday. Awesome. All right. And Ashawn, you're okay? Or all good?
Goodbye.
Oh, bye. Bye. Awesome. And Ashawn, you're okay?